Okay. My name is Takayuki Shuku from Okayama University. Today, I'm going to be talking about this topic: large-scale data-driven site characterization using geotechnical lasso. Okay, so in the keynote lecture by Professor Poon, he briefly explained G-lasso and briefly showed some results by G-lasso. So in my presentation, I talk about a little bit more detail of G-lasso, and I also quickly show the results of benchmarking using G-lasso. Okay, so this slide shows two site characterization methods. One is a polynomial regression-based method, and another is G-lasso. So in polynomial regression method, the trend amongst data is modeled by the linear combination of this kind of continuous basis function. And since the basis function is continuous, you can get this kind of smooth curve. On the other hand, in G-lasso, the trend among the data is modeled by the combination of piecewise function. Unlike continuous basis function-based method, piecewise functions can capture this kind of abrupt change in the data. So this is a big difference between two methods. So G-lasso estimates obtained by minimizing this kind of objective function consisting of two terms. First is linear least square terms, and another is regularization term. So if we don't consider this regularization term, so G-lasso estimates can perfectly match the observation data. So this is just copying the observation data. But this is not what we want to do in site characterization. What we want to do is to estimate the hidden structures or hidden trends among the data. So by minimizing this objective function, we can get this kind of reasonable trend. But in addition to this reasonable trend, G-lasso also gives us another useful information. So this term indicates a first order difference between two neighboring parameters. In this case, x1 and x2. So if these two values are similar and same, so this term becomes 0. And if this neighboring two values are not similar, are different, so this term becomes non-zero. So the location of non-zero can be considered as a boundary of the layer in the this kind of depth profile, and based on this kind of information, we can discuss the stratification without any other information. So, so the biggest advantage of using G-lasso is we can achieve trend estimation and stratification simultaneously and consistently. So these are the application example of G-lasso to 1D site characterization problems. And so lambda is a very important parameter that controls the complexity of the trend. And so, determining lambda is really important, and it's a bit difficult. And determining lambda can be considered as training in the context of machine learning. And in G-lasso, we use L-curve method. This is an empirical method, though, to determine the lambda. Okay, so lasso is a very attractive method for site characterization. Let's think about application of G-lasso to large-scale problem. I mean, benchmark example. So this is a objective vector and matrix expression of objective function of G-lasso. And Y is observation vector. The dimension of this vector is less than 700 in benchmark. In benchmark examples, this is not so large. And X is 40,000. This is the same as the number of unknown parameters. I mean, degree of freedom, 40,000. This is not so large. However, the matrix is large because to model the matrix, you have to consider all three directions. So in this case, the matrix, the size of the matrix is 120,000 times 40,000. So yeah, I'll show you the size of this matrix. So if you use double precision to represent the value, you need about 40 gigabyte to store this B matrix. And if the number of unknown parameters is 100,000, you need 300 gigabyte to store this one B matrix. So this is impractical. And in addition to space complexity problem, there is another serious problem that is time complexity. So in G-lasso, we use the algorithm called ADMM to minimize this objective function. And ADMM requires matrix operations such as matrix vector product and matrix product. But when we naively solve the benchmark examples using lasso, it takes enormous amount of time. So for example, okay, let's think about matrix vector product B by X. So it takes about 142 seconds. And in ADMM, we have to do this operation many times, like 1,000 and 10,000. So this is impractical. And yeah, matrix operation takes more time. For example, if you want to calculate this operation, it takes about 14 days. So this is also impractical. So we have to deal with these issues, time complexity and space complexity. So in order to address these issues, we take the advantage of sparsity of B matrix. So this is an example of B matrix. So as you can see, most of the entries of B matrix are 0. And in order to reduce the memory consumption, you should store non-zero entries. Actually, there are several methods to efficiently store the sparse matrix. So in G-lasso, we used CSR format. In CSR format, one matrix can be represented by 3 one-dimensional vectors. Okay, so by using CSR format, we can reduce the memory consumption. So if we don't use CSR format, it needs 40 gigabyte. But by using a CSR format, we use only 4.6 megabyte. And by using a CSR format, we can reduce the computation time. So for example, this matrix vector product takes about 142 seconds, but it takes about 0.007 seconds by using CSR format. So Taking advantage of matrix sparsity, the runtime and the memory requirement of the GLasso become scalable. So this figure compares the computation time between GLasso and GenLasso. So GenLasso is our package for uh, uh, for performing a lasso. And as you can see, GLasso is much faster, and GLasso can handle a large amount of data compared to GenLasso. So now GLasso can analyze these benchmark examples. So I quickly review the setup of benchmark examples. So we created 4 benchmark examples, G1, from G1 to G4. And G1 is the simplest and G4 is the most difficult, I guess. And available data are quantitative resistance QD and sleep friction FS and solid behavior type index IC. And IC is calculated using these equations, but I won't explain the detail. And the benchmark task is to map 3D stratigraphic profile and also to estimate engineering property. So in this case, QT in 3D space. And training set and validation set, I'd like to skip this slide. Okay, so we created 12 benchmark examples, and I applied GLasso to all the benchmark examples. So I quickly show the all the results. Okay, so these are the results of G1 T1 benchmark, and top indicates the results of QT, and bottom indicates the result of SVT. And in these figures, so this red thick line indicates mean value of the data used to generate a random value. So I mean, this can be considered as a true value, true trend. And this continuous thin black line indicates data. And this dashed line, blue line, indicates lasso estimates. So as you can see, even if we use training set 1, lasso gives us a very good result. So yeah, and so of course T2 and T3 we can get a very good result. So I guess this benchmark example is really easy to solve, and I guess very how can I say, naive method can work in this example. So how about the computation time? So we use this spec of computers used to analyze these benchmark examples, and it takes about 3.5 hours for training and 0.5 hours for getting the final result. So I mean, 4 hours. It took 4 hours in total to get the results of G1 T1. And these are the results of G2 T1. And yeah, results are not so bad, but as you can see, there is a big difference between lasso estimates and data and true trend. But so GLasso is basically how can I say, good at interpreting data, and is not good at extrapolating. So number 18 is located around the edge of the model ground. That's why basically to estimate the profile around the edge is might be a bit difficult. However, if you use a T2 training set, the performance improves a lot. So as you can see, GLasso gives us a very good estimation. And these are the results of T3. we cannot see a very big difference between T2 and T3 results. Okay, so this is a performance summary sheet, and in this example, it takes a longer time compared to D2 benchmark example. It takes about 11 hours in total to get final results. And these are the results of G3T1. Again, it's a bit difficult to estimate the solid profile around the edge of the model ground. But if we use T2 training set, the performance improves a lot. And again, T3 is not so different from the results of T2. And this is a performance summary table. And in this benchmark, it takes about 8 hours in total to get the final result. Okay, so this is a last benchmark example. I guess this is the most difficult benchmark example to solve. So it seems like lasso estimates are accurate, but important thing in virtual ground 4, G4, is whether the method can detect the incontinuous layer or not. So yeah, but G4T2, G-lasso cannot detect the discontinuous layer. So yeah, it's very difficult because in G4T1 benchmark, we use only 3 CPT profiles, and only one profile have the information of discontinuous layer. So using T2 dataset, it's quite difficult to estimate the discontinuous layer. However, if you use T2 dataset, so G-lasso can detect the discontinuous layer. And yep. And the results of T3 are not so different from the result of T2. And this is a performance summary. And yeah, it took about 11 hours to get the final result of G4T1 benchmark example. Okay, so let me summarize my talk. In my presentation, G-lasso for large-scale problems is outlined, and I quickly showed the results of benchmarking using lasso. And in my opinion, G-lasso can give reasonable stratification and estimation of engineering property, in this case QD, within a reasonable time, less than 11 hours. But of course, there are a few disadvantages in G-lasso. G-lasso cannot handle multivariate parameters, and G-lasso estimate is a point estimate. So G-lasso cannot evaluate the uncertainty of estimate. So we have to work on this. Okay, thank you very much.